Hi, let's play a little bit with torch tensors. So first we activate our Conda environment. Then we go into the Python shell and import torch. Apart from torch, we should also import numpy to see how the numpy array looks like. So let's start with sample data. Let's say data is a list of numbers 1, 2. So if we do type of data, tells us it's a list. Now if we convert this into a torch tensor, we can do this by saying torch.tensor of data. If we now look at type of X data, it says it's a torch tensor. If we look at the data type by saying xdata.dtype, it tells us it's of type dtype torch.int64. If I look at the shape of X data, it tells me its shape is 2. So it's a single dimensional shape 1 by 2, so it just needs to say its shape is 2. We could have created this as a two-dimensional object by saying data is a list of lists, let's say 1, 2, comma 3, 4. Now again, this is still a list, but when I create this X data as torch.tensor of data, now my X data.shape is a 2 by 2 tensor and not just 2 tensor. The D type of X data remains to be int64. I can also create a numpy array, let's say A to be np.array from this data, from the same data. Now if I do a.shape, the shape is retained. If I do a.dtype, it tells me the data type is int32 and the type of A is a numpy array. So torch interpreted that data directly as int64, but numpy interpreted that data as default of int32. Now we can create a torch tensor from this numpy array by saying x of A torch dot from numpy of array A, and now if I see the type of XA, that's obviously a torch tensor. If I do a D type of XA, it is of torch.int32. That's because the numpy array A was of type int32. So there is a close relationship between numpy array and torch. If the numpy array is int32, torch will remain as int32. We can also do the shape of XA, and it is still a 2 by 2 tensor. On the other hand, if my data was, let's say, a list of lists, but this time of 1.0, 2.1, 3.2, 4.3, it's still a list of lists. Now if I do X data as torch.tensor of data, now let's see what the D type looks like. Now it says it defaults to a D type of torch.432. If we do the same call A of as np of array of data And now we look at a dot d type. It is of type float64. But if we do x of a from as torch from numpy of a, and then we do x of a dot d type, it is still float64. So whatever data type exists in numpy array is kept in torch, but what numpy reads from data or what torch reads from data directly can be slightly different in terms of d type. Now we can also create a new tensor by retaining the properties, which is the shape and data type of the input argument tensor, unless we explicitly override it. For example, I can create a array or torch tensor of ones by saying torch dot ones like, but then pass in the argument x data. And now if I see x ones dot d type, it is of type float32, because if I say x data dot d type was also float32. On the other hand, if I say x ones is torch dot ones like x data, but if I say d type is equal to torch dot float 64. Now if I say x ones dot d type, I have explicitly cast this as a float64 object, so it tells me that its d type is float64. Although the underlying data is still a ones object, so it's all ones of size x ones dot shape as a 2x2 tensor. Now apart from ones, I can also create a tensor with random values by saying x rand equals torch dot rand like x data with, I can say, let's say d type equals torch dot float32. And now xrand object is a 2x2 tensor, because we can see the shape of xrand as a 2x2 tensor, and we can see the d type of xrand as a float32 object, because we explicitly cast that object to be a float32 object. If on the other hand I had done float64, now xrand would still be a 2x2 tensor, but now the d type is float64, although the data type of x data is float32. So we created a random tensor which has the same shape as x data, so it's a 2x2 tensor, but instead of getting the data type as float32, we can explicitly cast it as a float64 tensor. Now apart from shape and d type, each of these objects has another attribute called device, and that tells us where is this tensor located. So if I say xdata.device, it tells me this tensor is currently on CPU. If you have a GPU on your machine, you can push the tensors back and forth from CPUs to GPU, and that allows you to speed up computation by pushing the tensor on GPU. To test whether Torch sees whether this system has GPU or not, you can say torch dot CUDA dot is available, this function call will return me true or false. In my case, it returned false because I don't have a GPU on this machine. If I had a GPU on this machine, I could have said my X GPU tensor is X data tensor dot to CUDA, like so. But because I don't have a CUDA GPU on my machine, this gives me an error. You can also combine tensors using the cat call. So for example, if I say my tensor y is torch.cat of, let's say, x data and again x data, but I'm concatenating along the dimension 1. So now if I look at x data dot shape, it's a 2 by 2 tensor, but y dot shape is a 2 by 4 tensor, and we can see that here if we print out x data and if we print out y, it has concatenated along dimension 1. So keep in mind, dimension 0 is going vertically down along rows, dimension 1 is going along columns from left to right. You can also do matrix multiplication by saying, for example, M is a matrix multiplication of this tensor with this tensor. So I'm multiplying two matrices, a 2 by 2 matrix x data with the 2 by 2 matrix x data, and the result is M. So my M is still a 2 by 2 matrix, and M dot D type is still float 32 because x data dot D type is float 32. I can also call the same multiplication by explicitly saying M equals x data dot mat mul or matrix multiply by x data, and again my answer is the same, 7.72, 7.72, 11.13, and so. But if we instead want to do element-wise multiplication rather than matrix multiplication, then we can do M equals x data star x data. Now if I print out the value of M, that's very different because now we are doing element-wise multiplication. So if I go back and print x data, I am doing element-wise of two x datas here. So 1 will get multiplied by x1, and that gives me 1 here. 2.1 times 2.1 is 4.41, and like so. You can also do things like sum or aggregation. For example, if I say x data dot sum, that tells me that my total sum of all the elements in the tensor is 10.6. I can also call x data dot t to transpose the matrix. So remember, x data was 1.1, 2.1, 3.2, 4.3, and now by doing a transpose, the rows have shifted to columns and columns have shifted to rows. I can also add a scalar to the array tensor by saying x data dot add, let's say number 3. Now since x data was 1, 1 plus 3 is 4, 2.1 plus 3 is 5.1, 2.1 plus 3 is 5.1, 3.2 plus 3 is 6.2, and so. So this way we can do simple math on these tensors.